So in last lecture, we studied about the hydrostatic force on inclined plate. Okay, hydrostatic force on this inclined plate. Before this, we studied this hydrostatic force on horizontal plate. So for horizontal plate, it was simply this formula. Hydrostatic force is uh, pressure multiplied by area, or rho g h a, or the weight of the fluid above the plate till free surface. Weight of the fluid, this fluid. Okay, this weight of the fluid. So this is the case when it is horizontal plate. Now when it is inclined plate, the force on the hydrostatic force on inclined plate can be given as rho g a, the area of this plate, and hg, the height of center of gravity from free surface. Okay, vertical height. This is the vertical height from center of gravity, means from free surface till center of gravity. Okay, and one more important point, cp, which is center of pressure, which is known as the location. It is known as the location where the hydrostatic force actually acting, and it will always lie below the center of gravity of this plate. And the location, the location of this cp, which is yp, can be given as yg plus moment of inertia about x-axis of this plate, that too passing through center of gravity, divided by yg multiplied by area of the plate. Okay, so these are the things which you should remember. Now coming to curved surface, you see we have and few students have doubt also regarding this flat plate is there. No, this flat plate, it can have a rectangular shape like this. Okay, and fluid pressure is acting like this. So it can have, from this view if we see, it can have the rectangular shape. It can have this circular plate also. Still this is plate only. So some students get confused that if it is a circular plate, then you use the formula for calculating the hydrostatic force for this curved surface. Curved surface is this one actually. And if you see from here, it will look something like this, which is a part of a cylinder. If you see, it is a part of cylinder, and here the hydrostatic force is acting. Okay, so this is curved surface. From this view, if you see, you'll see this curved surface. But in this circular shape, if you see from this view, if you see, still you will able to uh, still you will see a face like this only. Even if it is circular, from this view you will see like this only. Okay, so this thing is important, because when you use the formula for calculating your hydrostatic force, there it comes a, which is the surface area. Now if it is circular plate, then you will have to use pi r square. If it is a rectangular shape like this, then accordingly half base multiplied by height you will have to use. Okay, for area calculation. And also to know the location of this yp, location, you need I xx about center of gravity. So you should know what is the I xx about center of gravity for circular plate, and you should know what is I xx about the center of gravity uh, for this triangular plate, and that you will have to use here. Okay, so this is the point which you should note here actually, because some students have doubt, like if in problem if it is given a circular plate, they assume that it is a curved surface, or that this fluid is exerting pressure, and that is not the case. Curved surface means when you see from here, it will look like this, some curve, and here if you see, it is flat one, means if it is a flat plate, flat plate, and its shape can have a shape of circular figure or a triangular figure. Okay. Now coming to the third category. So you see, we have studied till now. First was, you see, plane surface, and under this plane surface, first was horizontal surface. Okay. First was plane surface. Under plane surface, we studied horizontal surface. So this is the horizontal surface. Under plane surface only, we studied inclined surface. B is inclined surface. Okay. So this is the inclined surface. Okay. B. Now C is this under flat plate category, we have seen horizontal and inclined surface. Now third or the other category we have is hydrostatic force on curved surface now. Okay. So now we'll study about curved surface. So you see, curved surface means when you see from this side, you'll able to see this curve. Now you can imagine that this is a part of a cylinder. Okay, so gate is something like this. Okay, and it is a part of cylinder. Now here if you see, okay, what all the basic differences we are seeing till now. Again, I will explain. You see, when it is horizontal surface, the main difference comes with the distribution of pressure only, because force is always pressure multiplied by area. But if this pressure is constant or uniform, then you can directly put that value and multiply by area. Area is anyway for that figure, and you can calculate that force, hydrostatic force. So in case of horizontal, the pressure was what? Uniform. Everywhere pressure is rho g h only, uniform. And that's why you can use this P in place of P, you can write rho g h and multiplied by area. In case, so here in horizontal case, the pressure is uniform. In case of inclined plate, this pressure is not uniform. It is varying. Here it is 0 and here it is maximum. And that's why the center of pressure is below our center of gravity. So here the pressure is not uniform. Okay. And hence we integrated and we found the equation for hydrostatic force. Now next we'll see the curvature, curved surface. So here if you see, again the pressure is varying, and one more thing, if you notice here, the direction of this is also changing. Okay, so again I will talk about direction. You see here the direction is vertically downward. All direction is vertically downward. Okay, in case of inclined, although the pressure is varying, okay, but direction is in normal to this plate only, normal to this plate only, in this direction. All this pressure line what I'm showing here, all are normal to this. So all are in same direction only. Okay, so this is although the pressure intensity is varying, but direction is same. But when it comes to circular surface, you see, because pressure always acts normal to the solid body, so at this point it is in this direction, horizontal, and you see it is keep on changing. You see, it is every time it is changing, and it is vertically downward. Okay, so here intensity is also changing, and here direction is also changing. Okay, so that is the difference. Now to calculate the hydrostatic force for in case of this curved surface, what we do is, we first like the this is let's assume this is the hydrostatic force F. Finally we'll get hydrostatic force F, will get. Okay, now we can resolve this into two parts. First as horizontal component of this force, hydrostatic force, and one is vertical component of this hydrostatic force. So we'll calculate the horizontal force separately, and vertical force separately, and then to calculate this net force, what we can do is we'll simply do this vector addition, FH square plus FV square. Okay, and like this we can calculate the net force here. Now the next task is how to calculate the horizontal force. Okay, now to calculate horizontal force, this FH, what we have to do is simply you see this curved part from here. Okay, how it will look like? It will look like a rectangular plate like this. From this view you have to see, from this view. So how it will look like? It will look like a horizontal plate like this. Okay, and then you can apply that the equations for calculating hydrostatic force, what we have used for that inclined plate we have seen. No, that inclined case, the theta is, I mean, like it is having some theta. For vertical case, the theta will be what? 90 degree. It will be 90 degree. So that same formula, this same formula you can use. What we have calculated here, you see, the same formula you can use. Only thing, this theta will become what? 90 degree. That's all. Okay, and then you can calculate this F, which will be what? Which will be the, this is the shortcut. Okay, otherwise you will have to integrate and find all those things. This is simply a shortcut to calculate the hydrostatic force, the horizontal component of hydrostatic force. So to calculate FH, you simply see from this direction and you see what you are seeing. You will see a rectangular plate like this, whose height, this height will be what? Whose height will be the this particular height, and width, which will be nothing but your radius only. Like if this is your center, so this represents, this vertical line represents what? Radius only. So this height will be radius of this uh, cylindrical part, and this width which will be given in the problem. How much depth is there or width is there, that will be given in the problem. So let's say if the width is some b. Okay, then the projected area, this area will be what? The area will be the projected area, which is AP, is equals to R multiplied by B. So this will be your projected area. Okay, this will be your projected area. Now how to calculate FH? That same formula, rho multiplied by G multiplied by area multiplied by HG. Now area will be what? The projected area, not this circular part wala area, not this circular surface area. No, or this curve, sorry, the curved surface area. No, not that one. The projected area. From here you see how it looks like. It will look like a rectangular surface whose projected area will be this height, which is R, and depth will be B. So R multiplied by B. This is the projected area. Okay, R multiplied by B. So this is how you can calculate the horizontal component of your uh, this hydrostatic force. Okay, now how to calculate the vertical component? Now to calculate vertical component, what you will have to do is simply calculate the weight of the fluid above this curve, above this curved surface. This curved surface is there now. You simply calculate the weight of this fluid. What you can see here, this figure you can see now, this one. You calculate the weight of the fluid. How you will able to calculate the weight? Weight is what? Density multiplied by volume multiplied by G. So density of fluid, anyway you will know. G, anyway it is a constant value, you know. The main task is volume. Now how to calculate volume? It is also simple one. You see, if you able to calculate this area, this area multiplied by depth B, that will give you the volume. Okay, now you can say, sir, this is not an easy task to calculate this area. Okay, it is not an easy task. They can give some regular figure to calculate, or some easy figure to calculate. Here also you can calculate the area. Like, you can assume this as complete rectangle. You can assume this as complete rectangle. Then you calculate this complete rectangle area. Okay, then you subtract this much area. Okay, that would be easy for you to calculate. Okay, that would be easy for you to calculate. Like that, you can subtract and you can calculate this area. Okay, once you calculate this area, and then you multiply with this b width, you will get the volume, this volume, and then multiplied by density multiplied by g. This will give you what? Weight of the fluid above this curved surface. Weight of the fluid above this curved surface. Now, and logically also, this should be the vertical component, because the weight will act vertically downward, so that much vertical force it will exert on this curved surface. So now you know the vertical component and you know the horizontal component. Now now what you can do? You can calculate the net force, net hydrostatic force, which is Fh square plus Fv square. Simple. Okay, this is how you can calculate your hydrostatic force. Is it clear? Okay, now next is you may see this type of gate where fluid is exerting pressure from this direction. Okay, what is the difference? You see, this is the curve and fluid is above this curved surface. So pressure is acting from this direction. But in this particular case, fluid is exerting pressure from this direction. So for this particular case, what you can do is, you simply, to calculate the shortcut I'm telling you, what you do is, horizontal will remain same. Horizontal component will remain same. You see from here, it will look like a rectangular plate for you, whose height is again the radius, depth b will be given. So horizontal component remains same. What for vertical component, what you can do is, simply you project from this point, you project till this free surface, project one line, and from this line you project till this free surface, and you calculate this area, and this area multiplied by this depth, that will give you the vertical component, Fv. Okay, with the derivation we can prove also, because you can ask, sir, here what we are doing is, we are assuming a hypothetical fluid here. It is filled with this much hypothetical fluid, and that same fluid, this fluid only, it is filled here, and it is exerting force like this, pressure like this. Okay, and you can calculate that vertical component, and with derivation we can prove also, because with integration it will come. And just quickly I will explain this part. I will not go into the derivation part, but quickly I will explain how logical it is to calculate this force, vertical force. You see here, it is having a pressure like this at this point, and then it is changing the direction like this. Okay, now pressure is continuously changing. So at this point, what is the pressure? This much, rho g. Let's say this height is h1, so rho g h1, And when it comes to this point, let's say if this height is h2, here the pressure is rho g h2. Okay, so when you will calculate this weight, you see weight comes from rho multiplied by g multiplied by h, okay, and then multiplied by area. Okay, that means if I break this volume, this volume is equals to, let's say, area multiplied by height. Now this height and this what you will do is you will take a strip and then you integrate this one. It will come and you will integrate from here to here, and pressure will be rho g, that h. Okay, just a small strip I will take. Let's say this is the strip, and dh, and the height for this one from here to here is h. So pressure exerting here is what? Rho g h. Okay, here and you, what you will do, you will integrate from this height to this height. Okay, and rho gs, this is the pressure, and then multiplied by area for this will be what? A small strip which will be, let's say, dh. This strip width is dh, and the depth will be b, and then this will give you what? Complete hydrostatic force, df. Now you can integrate this one. When you will integrate this one, the answer what you will get here will be equivalent to the weight of this fluid. Okay, like this you can calculate. So no need to do all these integration part. You simply calculate, assume a fluid which is which is above this curved surface. It is filled with this fluid, same fluid above this curved surface. You calculate the weight of the fluid in similar manner, and then you calculate the weight, you will get the same answer. Is it clear? I'm not explaining you, or means explaining you that integration part and all those things, because uh, from HL point of view it is not important. Instead of wasting time in integration and all those things, we can uh, solve few questions instead of that. Okay, so that's why I'm just trying to save some time here. Even if you want to know that derivation and all those things, you can refer your books, and if you have doubt you can ask, no problem. Okay, now next is buoyancy topic. This topic will complete and then we'll start solving the MCQs. Now buoyancy, when a body is either wholly or partially immersed in a fluid, then the hydrostatic lift due to net vertical component of hydrostatic pressure force experienced by the body is what? Buoyant force, or this phenomena is known as buoyancy. Okay, now this thing I will explain you here. Let's say a body is immersed. This body is immersed here in this fluid. Now this fluid will exert some force on this top surface. Let's say horizontal, here it is acting some pressure, and here also in this space also some pressure is acting, and because of that some force will come. And if both area are, just for explanation I have taken this regular figure, otherwise it can have some irregular figure also, but the result will come same only. So because that horizontal components will cancel out each other. Okay, and because there will be no horizontal force difference. Okay, but when it comes to vertical forces, so if I see this phase, the force acting is F1, and just below this phase, this one, the force acting is F2. Now force can be given as pressure multiplied by area. Now let's say this area is A. Okay, now pressure on this surface, to calculate F1 I need pressure here on this surface, which is what? P1 multiplied by area. Now P1 will be what? P1 will be how much height below the free surface? Z1 height. So P1 can be written as rho g Z1 and then multiplied by area. Okay. Similarly, the pressure will act in this direction from bottom, and that's why the force will act in this direction, F2. Now F2 can be calculated as rho g now Z2, because here at this level the pressure will be rho g Z2 at this level, and here the pressure is rho g Z1. Okay, so the pressure at this bottom wala phase is rho g Z2 multiplied by area. Now if I calculate the difference, F is equals to F1 minus F2, what I will get? Rho GA Z2 minus Z1. So if I calculate F2 minus F1, then Z2 minus Z1. And obviously Z2 is greater than Z1. So this thing will come a positive force, and as it is positive and F2 minus F1, so net force is in which direction? It is in this direction. So this direction, the force, net vertical direction force here, the difference of F1 and F2, we are getting a net vertical direction force, is known as this buoyancy force. So because of this pressure difference, this height and pressure difference, a force, vertical component force is coming, and that is our buoyancy force, which helps us in, pushing this body in upward direction. Now there is one more force which I have not considered here. Now there is one more force which is the weight of this body itself. Weight of the body itself. So now if weight of this body, weight of the body is greater than this buoyancy force, then it will sink. And if buoyancy force is greater than weight of the body, then it will float here. Okay. So this is the two condition what we will study in buoyancy. First condition is when uh, uh, weight of the body is greater than buoyancy force. Then in that case, the body this body will submerge. Okay, so that will be a submerged case. And when the weight of the buoyancy force is greater than this one, it will be not greater actually. I should not say greater because it will float here, no? So it will be equal actually. When buoyancy force is equals to weight of the body, then it will float here. Okay, like that. So from here only we'll have a condition. We can have a condition when this body can submerge and when this body can float here. Okay, so that those two parts only will have to study here. So up to here, is it clear to everyone? Now next is the formula for to calculate buoyancy force. You see, just now we have seen FB is F2 minus F1. Now F2 minus F1, this is F2 minus F1. If you rearrange, what you will get, rho F G. Rho F is what? See, fluid is exerting this force, no? So this density should be density of fluid. Okay, in calculation of this buoyancy force, this rho F, this density should be the density of fluid, because buoyancy force is the difference of this F2 minus F1 which is exerted by the fluid. So this should be F rho F first. This is first thing we should note. Next is G is anyway constant. Then when I club this two, if you multiply A multiplied by Z2 minus Z1, then I will get what? Volume. And that volume is nothing but the submerged part. Here you can see it is completely submerged, and that's why it will be the volume of this body itself. But what if this body is floating like this here? If it is floating like this here and only this much portion is submerged, then what you will have to do is what you will have to do is, you will have to calculate volume of this much solid only. Okay, this much solid volume you calculate, and then multiplied by G, then multiplied by density of fluid will give you the buoyancy force. Because here, you see, when you will calculate the this Z2 minus this Z2 minus Z1 is there, no? So Z1 is like this is the free surface here. So that will become 0 only. And Z2 will be this much height. This will be your Z2. Okay. So Z2 multiplied by area multiplied by rho F multiplied by G will give you what? Only this much volume. Okay. So that's why we should take care here while calculating the buoyancy force. And from formula, we can note here that it is independent of density of the solid body. Buoyancy force, I'm not telling you whether the body will float or not float. It will depend upon float or submerge. It will depend upon the density. It will not depend upon the density of the body. It is not like that. I'm only talking about the buoyancy force. So with the formula, you can see it is the buoyancy force is not depending upon the density of solid body. It is depending upon density of fluid. I'm talking about only buoyancy force. So they can ask question like this. Buoyancy force depends upon density of fluid, depends upon density of solid body, depends upon both, or any other option they can give. So you should make a note of this point. Okay. Now, next point you should note here is that the buoyant force acting on body is actually equal to weight of the liquid displaced by the body. This is also very important point to be noted here. You see, when I will calculate this thing, what is this? Rho F multiplied by submerged body multiplied by G. Now density multiplied by volume is what? Mass. Mass of what? Fluid multiplied by G. Mass into G is what? Weight of the fluid. Now weight of fluid, what? Which fluid? The part which is displaced. Like if it is, yeah, I'm having this figure. You see, this much portion is submerged, na? Only this much portion is submerged. So initially, this much fluid would have been there, and which has been displaced here, and solid has carried that particular, that much fluid has displaced. So you are actually calculating the weight of the fluid which has displaced from its position due to introduction of this solid body. Okay, so that is your buoyancy force. Okay, rho f g multiplied by VSB. Okay, so they can ask in the option also, they can ask this thing: buoyancy force acting on the body is equals to weight of the liquid displaced by the body. Okay. Now, when some body is, let's say, floating here, or even if it is submerged, you can feel that its weight has reduced. But actually its weight is that it remains same only. Only thing is that one vertical component, which is the buoyancy force acting on this body, and because of which we feel that the net weight of this body has reduced. This is only because of the buoyancy force which is acting in vertical direction against the direction of weight of the body. Okay, so because of this buoyancy force, net weight of the submerged body is reduced from its actual weight by an amount that is equals to buoyancy force. So they can ask, let's say, they can ask initial weight of the body is, let's say, 30 Newton. And buoyancy force is, let's say, 10 Newton. Okay, then what will be the weight of this body inside this when it is submerged like this? What will be the weight of the body or apparent weight of the body? Then what you can do, you can simply do this 30 minus 10, so it will be 20 Newton. That will be the weight of the body inside this fluid. So when you will, or they can ask, when in air with spring balance you are measuring the weight, it is coming 30 Newton. When you are measuring with this same spring, when you are measuring inside, it is showing 20 Newton. Okay, it is showing 20 Newton. Why the difference is coming? Difference is coming because of this buoyancy force. Is it clear? Now, we have two cases. One is submerged body, another is floating body. Okay. In case of submerged body, what happens? Buoyancy force is less than the weight. If weight is more and buoyancy force is less, this will submerge. Okay. And when the weight of the body and buoyancy force is equal, it's not like FB is greater than, it cannot push outward this one. Okay, net force cannot come like this. So if FB is equals to weight of this body, then it will be a floating body case. Okay, now from this we can say that buoyancy force is equals to, like if you want to calculate what is the, now if you want to calculate what is the buoyancy force acting on this floating body. Okay, if let's say if it is given in problem, the weight of this body is, let's say, 30 Newton, and if they are asking what is the buoyancy force here, and this is floating, it is not submerged. So what we know is that it can float only when buoyancy force and weight is equal. So if it is given weight is 30 Newton, buoyancy force should also be 30 Newton only. Then only it can float here. Okay. So this is the case for floating body. Now, when it is submerged body, obviously FB is less than weight. Okay. Now, next is we should understand what is center of buoyancy and what is center of gravity. So you see, center of gravity is the center of, center of gravity where the weight of this body is acting. It is assumed that here only the weight of this body is acting, which is this G. Okay. Now center of buoyancy, which is represented by B, this B, center of buoyancy. Center of buoyancy is the center of the displaced fluid. Buoyancy force is what? It is the amount of, it is the weight of the fluid which is displaced. So center of that. So how to calculate that part is, you simply see here it is submerged, no? So it will coincide here. But if it is floating, so you see this much part is only submerged or inside the fluid. This much part is above. So what you can do is, to calculate this B, you just simply calculate half of this height. Half of the submerged part. Half of the submerged part is this much. So this is the location of your B. Okay. Like if this height is, let's say if this complete height is given 20 centimeter, and this height is given, let's say, 12 centimeter. Okay. Then B will be what? From bottom, it will be, from this bottom, it will be 6 centimeter. From bottom, it will be 6 centimeter. And G will be what? G will be half of this. So from bottom, it will be 10 centimeter. This is how you can calculate the location of G and B. So when it is floating, this is your center of buoyancy location. And when it is submerged, this two will coincide, obviously, because G will remain here itself. And B will also be half of this. See, completely submerged, so half of this, which will be here only. So in case of submerged, in submerged wala case, both will coincide. But in case of floating, we'll have to calculate this thing separately. So figure ka half of this figure will give you G, and submerged ka half will give you B. Is it clear to everyone? Okay, now next is, so one thing we have noted here is that G location is not changing. Here also it is half of this figure, or half of the height of this figure. And here also it is half of the height of the figure. But B location actually changes, always changes. You see, if it is completely submerged, it is at the center. But when it is partially submerged like this, it is here. If let's say if it is submerged here up to here only, then half of this somewhere here, like this. So B location always changes, but G will not never change. Okay. So here only we'll have to see the stability condition. Like if let's say this is my boat, let's say this is my boat. So what now you'll, if you are designing a boat, you should see whether it will overturn or whether it will be stable, or what happens to this boat when it is floating in a water or in a sea. Okay. So here comes the stability condition. So stability can be studied in three categories. One is unstable equilibrium, another is neutral equilibrium, and one is stable equilibrium. So what is unstable, neutral, and stable equilibrium? So you see, first we'll see stability of a submerged body. Okay, first we'll see the stability of this submerged body, and then we'll see the stability of floating body. Now you see, first we are focusing on this one. Now, if the density of this solid body is uniform, density of solid, density of the body, I'm telling, density of body is uniform, then the center of gravity will lie here only at the center. Okay. But what if, let's say this much part is made of some other material and this much part is made of some other material, like, or let's say this much part is made up of your iron and this much part is made up of wood. So now the density is different, this much part density is different, this much part density is different. So whether the G will lie at center of this one, mid of this one? No, in that case it will not lie at the center. So obviously it will displace toward the heavier density side. So wood is lighter and this is metal, iron. So it, instead of G lying at the center, it will lie below the center point. So G will lie somewhere here in that case. If two bodies are made, this single body is made up of two different material. But your B will remain at center only, because B can be calculated by the volume displaced. And here this much volume is displaced, this much height of volume is this much height of water is displaced, so it will be center of this only. So B will remain at the center, but G will displace. Okay. So again, I will tell you, G, location of G will remain at center if the density is uniform. If density of body is uniform, G will lie at center, geometric center. But if B, density of body is non-uniform, like if it is made up of two different material, then G will not lie at center. G will not lie at your geometric center. Okay, this is the first thing. This is about G. Now I'm talking about B. B will always be calculated with by noticing that how much part is submerged inside the fluid. If it is completely submerged, then half of that. Simple. If it is this much submerged, half of this much. That's all. Okay. This is how we calculate the location of B. So is it clear to everyone how to calculate location of B and how to calculate location of G? Am I explaining too much, or uh, shall I move fast or slow? Anything you can tell me. Okay. Now stability. So first we'll see the stability criteria. This is very important. Generally in GATE exam also, in 1 mark question, like from, if you notice, question paper from 2008 to 2015, like that, this is one of the favorite question of GATE. Every alternate year they are asking this question in 1 mark. Okay, so the stability is very important part. So you see, first we'll see the stability of submerged body, and then we'll see the stability of floating. So first is submerged wala. You see, let's say this circular shape is there, no? This sphere, let's say it is a sphere, and it is inside fluid. This is submerged, for submerged body, no? So it is submerged inside fluid. This is the free surface, let's say. It is completely inside. Now, if geometric center is here, let's say this is your very heavy high density material, and this is yellow wala portion is low density material, then obviously the G will shift above and B will remain at the center only, the geometric center only, because it is completely submerged, no? So this complete part is submerged. So as this is complete, as complete part is submerged here, so B will always lie at the center. So in all the cases here, B will lie at the center. Okay, because this is a case for complete submerged body. Only location of G will change. Okay, and and with that change we'll see the stability criteria. Now first, let's say this is heavier part and this is lighter part, so obviously G will shift upward. Okay, it will be somewhere here. Now with this by knowing that heavier part is here and low, this lighter part is in downward direction, obviously you, by seeing itself, you will tell, sir, it will overturn. Yes, it will overturn. It will overturn, and that's turn, and that's why it is unstable equilibrium. So mathematically also we should explain this thing. So let's say if we are giving some external moment to this body, external moment we are giving, so we are turning this body from outside. So when we will turn, what will happen? B will shift somewhere here. Okay, means geometric center only here itself, but G will shift something like this. Okay, so G will shift somewhere here, and B will be at center only, but G will shift something like this. Now at G, what happens? Weight of the body acts. At G, what happens? Weight of the body in downward direction acts. And at center of buoyancy, what acts? At B, what acts? The buoyancy force act. Now you see, it is about this point, it is forming a couple. So you have exerted a means moment in this direction, and it is forming a couple because of this forces in this direction only. So what will happen? This couple will, as this thing is assisting this moment, it will overturn. And what will happen? This heavier portion will come downward, and this lighter will go up. Okay, so this is unstable equilibrium. So unstable means when you are applying an external disturbance here, it is not coming back to its only original position. In fact, it is going to some other equilibrium condition, not previous equilibrium condition. So this is unstable. Same thing will happen if I apply ulta, just ulta. So W will shift here. So this is W direction, this is B direction. Again, you see in the same direction, you see in same direction you will get this moment, and this will overturn. So with external disturbance, disturbance, what is happening? The equilibrium is getting disturbed, and because of that, it is a unstable equilibrium. Okay, it is unstable equilibrium. What is your doubt? Just there will be no hinge point. Like means anybody, if you are rotating, if this has shifted and this is the buoyancy force, so it will form a couple, no, some two parallel forces like this. So about their midpoint, wherever this location, about their midpoint, they will form a couple and they will rotate like this. There is no hinge point here. Okay, so this is your unstable equilibrium. But next is neutral equilibrium. Now what is neutral equilibrium? Let's say this is made up of single material, uniform density, single material, no black portion, you see, no heavier material. So you see, it will coincide. G and B both will coincide at center only now. So even if you are displacing, G is here only, B is here only, and W is acting vertically downward here, B is acting vertically upward. They are passing through same point, so they will cancel each other, and there will be no. So there will be what? There will be like, it will rotate, and in it will attain equilibrium in some other condition. First I will tell you that, let's say, what is stable, unstable, and neutral equilibrium with some other figure. Let's say if I have some ball here, if I have one ball here, if I display if I have a ball here and it is stable here, it is stable here. If I displace this ball, what will happen? It will go down and it will remain and it attain some other equilibrium condition here. So it will not remain here itself. Okay, so this is unstable case. Stable case is like, let's say this is the case, and if I have a ball, some ball here, and if I displace this thing, let's say up to here, this ball, what will happen? It will again come back and try to attain its original position. Okay, this is stable equilibrium. So when you are applying some disturbance, it is trying to come back to original position. Here when you are applying some external disturbance, it is going away from original equilibrium this thing, equilibrium condition. Now third is neutral. Let's say this is a flat surface, some ball is here. Now if you displace this one, it will move and it will attain some equilibrium condition here. Okay, so this is a neutral one. Okay, this is unstable one, and this is stable one. Okay, so Here if you see neutral equilibrium, you see when G and B coincides, then it is a neutral equilibrium. Now comes the stable equilibrium. In stable equilibrium, you see B is here. In stable case, what happens? This is the heavier portion, which is in the downward direction, and lighter one is here. So obviously the G will shift downward, and this is the geometric center. Now if I apply small moment here, what will happen? B at the geometric center, and as this has moved, G will shift here. Now you see G is here. This weight is acting like this, and buoyancy force is acting like this. Now you see it is ulta. I have applied in this clockwise direction. I have applied a moment in clockwise direction, but this couple is forming anti-clockwise moment. So it will resist your external disturbance and try to regain its original position. And that's why this is stable equilibrium. Okay, same thing will happen if you just try to rotate in ulta direction. In this direction, W will shift here, this will be shift here, so this will form a clockwise, and you have applied a anti-clockwise. So this is a countering moment. Okay, that's why if it is countering, then it is a stable equilibrium. If it is coinciding, neutral. If it is favoring, then it is unstable equilibrium. Now, but what they will ask is, this thing I have just explained you, but in examination, what they will ask, with the position of B and G, you will have to answer whether it is unstable, neutral, or stable. So you just remember one thing. This anyway you will remember, that if it is coinciding, it will be neutral. For stable, you remember if G is below B. If G is below B, it is stable. Ulta of this is unstable. Okay, so you just remember this thing. If G is below B, then it is stable equilibrium. Is this point clear? Now next is stability of floating body. This is the last topic. Okay, after this we'll start our this numerical, because after this our next topic is fluid kinematics. Okay, so first we'll solve not numerical, sorry, MCQs, and then we'll move ahead to next topic. Okay, so stability of floating body. In last slide we have seen stability of submerged body. So in case of floating body, this is the floating body. You see this is free surface, this is your floating body. So what happens? Only this much portion is immersed here. This is the portion which is immersed here, and above this it is that portion is lying above the free surface. So here what happens? You assume this is your boat. You assume this is your boat. So what happens? It has a metacentric height, it has a center of gravity, it has a center of buoyancy, all these things. So here B, G, M, three things are there. In previous case, we had only center of buoyancy and center of gravity. Here one more center will come, which is metacentric height. Okay. So first we'll try to understand that one. Okay. So for that, let us understand from this figure. So let's say this is your boat, okay, and let's say this is the geometric, not geometric, this is the center of gravity G, where the weight is acting in downward direction. Okay, now here this is your center of buoyancy B, where the buoyancy force FB is acting. Now if it is in this condition, it is stable. Okay, now when we are taking the stable and unstable condition, this is the first stable condition, let's say, or equilibrium. It is in equilibrium condition, let's say, not stable, this is in equilibrium condition. Now I'm applying a moment from, or like due to some external uh, moment or external disturbance, this ship is overturned like this. Okay, because of this external moment, you see external moment in this direction. So because of that, what happens? This G and B, obviously this much portion you see initially, this much portion is below your water. Okay, but now if you see or no, sorry, here the free surface lies. Sorry, this is your free surface. This is your free surface. So you see initially this much portion is above your free surface. But when I have applied this moment, this much portion has come up and some portion has come down. And because of that, there is a difference in the portion of ship which is inside the water compared to this condition, and that's why the B location will change. B location will change here. Okay, G location will not change because this is the center of gravity of the whole ship, but B will change because now the shape which is in the part which is inside the water is this thing, and because of that the location of B is changed. Now this is your G, which is vertically downward. Now what we can do is, and this is your B, vertically upward. So from here we can take one vertical line, and this is your initial this wala line. Initial this wala line. So this is your initial this line which is passing through center of gravity. Okay, and this is your new line which is passing through new center of buoyancy. Now where these two meets, that is your meta center. Okay, that is your meta center. Now again, for stability, so what it is assumed that about this point only the ship is moving to and fro like this, oscillating like this. Okay, the ship is oscillating like this. So you see, again I have applied a clockwise. About this point I have applied external disturbance or external moment in clockwise direction. But now you see this is G and this is B, which is forming anti-clockwise moment, which is known as restoring moment. So this is in ulta direction. So this will help you in stopping the overturning of fluid, overturning of your ship, and that's why this is your stable condition. But let's say if your meta center lies here, because of some condition, if meta center itself lies here, then center buoyancy is here, G is here, then what is happening? In clockwise direction you are applying external moment, and you see this couple direction, this is also about this point, it is forming a clockwise moment only, which is a overturning moment. So it is in same direction, so this will overturn your ship, and it will overturn, okay, there. Okay, so this is your unstable condition. So in both the case, if you notice, B remains below G only here. So it is not the position of G and B will decide your stability condition in case of floating body. It is the location of G and M will decide. You see, M is above G and here M is below G. So in case of submerged wala part, relative location of G and M will tell you the stability condition in case of what? Floating wala part. But in case of submerged wala part, relative location of G and B will tell you whether the body is in stable or unstable or neutral equilibrium. Okay. Again, in both the cases, if G is below, you see G should be in below. G below B stable for floating for submerged, and M is above and G below This is stable when it is floating. This you remember, ulta you do for unstable condition. That's all. Okay. And if G and M is coinciding, that will be your neutral case. Simple. Is it clear? Now, for that, the last thing is period of oscillation. You see, if you have traveled in the ship, then this ship actually oscillates. The ship will oscillate. Like if this is the free surface here, this will oscillate like this. So when there is a oscillation, it has a time period of oscillation. So how to calculate the time period of oscillation? This is the formula to calculate the time period of oscillation. 2 pi root over Im divided by W multiplied by Gm. Gm is the distance between G and M. M was above, G was below. This is the distance between these two. I don't think they will ask the numerical base on this because it will take time. It's a time taking thing. So you just simply remember this Gm is the distance between G and M. Okay. Distance between this thing, G and M. This is your Gm. Okay. Which can be calculated by, you see, Gm Gm can be calculated with this formula. Gm is Iyy, which is the moment of inertia about y-axis, or the least moment of inertia wala, divided by immersed volume minus Bg. You see Gm, this is M, this is G, and this is B. And you want this thing. Okay. So this can be, you want this thing. So this can be calculated as Bm minus Bg. Bm is this complete height. This minus this will give you what? Gm. Now Bm can be calculated by this formula. This is nothing but Bm. Bm minus Bg. Bm can be calculated with this formula. I divide by immersed volume. Immersed volume is the volume which is inside your fluid. Okay. Minus Bg. Bg is half of this thing. Half of this distance. Simple. Half of this distance. Okay. For regular surface, it is like if it is a rectangular shape, half of submerged, you simply calculate, that will be your Bg. So it is very easy to calculate actually. But those things I don't think they will ask. Okay. I'm just explaining, if for safer purpose, like safe side, I am just explaining you. So this thing is Bm minus Bg. With this you can calculate the Gm. Now you note here is that this is your area moment of inertia. But in case of time period, in the calculation of time period, this I is what? This is mass moment of inertia. This is mass moment of inertia. So in calculation of time period, this I is Im, which is mass moment of inertia. But in case of Gm, this I is area moment of inertia. Okay. So with this, you can calculate your time period. So you see, if so, there is two things when you are traveling in a ship. There is two things. One is stability and one is comfort. Are they same? Can you say stability and comfort are same thing? You see, stability means it will never overturn. Stability means it will always come back to its this initial equilibrium condition. So it will never overturn. That is stability. Okay, that is stability. Comfort is how much time it is taking to move, like ship will move like this, no? Or like in this direction, if this is my ship, what happens? It move up, then down, up, then down, like this when it is moving in this direction. So how much up and down? So how much time it is taking to go up and then down? If it is, see, if it is frequently, very frequently going up, going down, going up, going down, will you feel comfortable? Will you feel comfortable? I am making sure that it will never overturn. Or even if it is in this direction also, will you feel comfortable? No. So comfort, you see, comfort will be when your time period will be very large. You see, when it is taking more time to go up, then very more time to come down. So to complete one oscillation, it's taking very means large amount of time, then it is comfortable for you. Okay. So to have more time period, GM height, the height of GM should be less. If GM is less, time period will be more and you will feel more comfortable. But when it comes to stability, you see, when it comes to stability, this is your stable condition. When GM is greater than 0, means more the value of GM, more the difference, more this height, more there will be a stability. So when GM is more, you will have more stability. But then time period will be lesser. Then you will not feel comfortable. Okay. So that's why if it is a cargo ship, like if you want to transport something, there stability is the main concern, because the material what you are transporting, that should not sink in the sea. Okay. So that's why the stability is more important there. So there we design with higher GM value. But when it is a passenger ship, there our this comfort is also important. There we try to, but we cannot sink. That is also a thing. So we should trade off between these two, comfort and stability. Is it clear? Is it clear to everyone? And this is that thing which I have already explained you in hydrostatic condition. Hydrostatic condition, or in fluid statics, what happens? Shear stress tau 0 is 0 and only normal stress acts, and this normal stress is nothing but a pressure. And in, if you want to denote it in Mohr circle, this is your vertical axis shear stress, this is your normal axis here. So this is the location of your hydrostatic condition, minus P. With a single point in anywhere in negative axis, you can show your hydrostatic condition. Okay. So with this, we have completed our buoyancy topic also. Now we'll try to solve few numericals based on this. Okay, from here we can start solving. Okay, so answer for 74. Answer of 74. Point in a immersed body through which resultant pressure of liquid. You see, again I will tell you. All these points I will again explain you. You see, metacenter. Metacenter is related to, see, first I will tell you the center of pressure in sequence. We have seen like when we have an inclined body, inclined plate like this, and fluid is exerting pressure over this. So we have center of pressure, CP, where this net hydrostatic force acts on this body. Net hydrostatic force F act on a body is your center of pressure. Okay, again I will explain you, just don't get confused with these things, the terms. You see, center of pressure. What is center of pressure? Where the hydrostatic force acts. Where this hydrostatic force act is center of pressure. Okay, this is the first thing. Next is this G. G is the center of gravity of this body. Okay, so centroid or centroid, where the this weight of this body is acting. B is center of buoyancy. Center of buoyancy, where the weight of displaced fluid is acting. Okay, weight of displaced fluid, the fluid which has get displaced from here, that is acting. That is your center of buoyancy. And metacenter, the last one, metacenter is a point about which this is moving. This is oscillating. Okay, so this is the metacenter is a point about which this body is floating and it is oscillating. Okay, about this point only it is oscillating. Okay, so this is related to your oscillation, metacenter. Okay, now again I will come back to the question. Read it properly and then again answer me. Yes, it should be center of pressure. You see, point in a immersed body through which resultant pressure of liquid. You see, when a body is immersed, about, or I will draw this view. This is all pressure is acting in this direction. So some resultant of all this pressure force will act on CP here. This is a submerged this thing, na? Submerged gate or submerged body only. Immersed body where a resultant of pressure of liquid is acting. Okay, resultant of pressure of liquid or force, resultant of pressure force also you can say. Okay, is it clear? Don't get confused with this definitions. Okay, next question. '76. This is 11th or 12th class question. If you see, resultant upward pressure of a fluid on a floating body is equal to weight of the fluid displaced. This is known as what? This is known as buoyancy force only. This force resulted upward pressure force is your buoyancy force. Okay, this is your buoyancy force. But this definition comes from where? From which principle? It is coming from your Archimedes principle. Okay, you should understand the difference here. They are not asking what is known what is the name of the upward force, net upward force acting on a body. That is your buoyancy force only. But they are asking, this is this definition. This is the definition. Now this definition is according to which principle? It is according to your Archimedes principle, which you have studied in your 11th, 12th class. Okay, now next 77 question. Yes, this is B, because this here it is asking resultant upward pressure of the fluid on a immersed body. So this is your buoyancy. 78. Why A and why B? One has answered A, one has answered B. What is the condition for stable equilibrium in floating condition? It is the relative location of G and M. You see, it is relative location of this. Okay, so and M should be above G. M should be above G. Okay. Okay. Next question you tell. Metacentric height. What is metacentric height? GM. GM is your metacentric height. So it is distance between G and M. So what should be the answer? I've told you, no, GM is your metacentric height, which decides the stability and comfort condition. So G, distance between G and M. G is your center of gravity of the body and M is metacenter. So distance between these two, distance between G and M is GM, which is your metacentric height. So A is the answer. 81. 81 is buoyancy force depends upon what? Mass of liquid displaced. Obviously, not the viscosity, pressure, depth inversion, all those things. Not mass of liquid displaced. 82. Are you able to see this question? Some is looking a little blurred. Center of gravity of the volume of liquid displaced by a immersed body is called. Yes, it is center of buoyancy. I've told you, no, that if this is your free surface and if some body is submerged like this, so here initially some fluid would have been here, and some fluid is present here initially, but now because of this solid body, the liquid displaced. So the same the amount of liquid which has displaced here, that only will create the buoyancy force here. Okay, so that's why it is written here clearly. Volume of liquid displaced by immersed body. Volume of liquid which is displaced by this immersed body. And that only is creating a buoyancy force here in upward direction. So center of buoyancy. 83. Okay, buoyancy force is actually means it is weight only, weight of the liquid displaced only. That is correct. More appropriate is weight only, weight of liquid displaced. Okay, 81, 83. Only one has answered. 83. Yes, answer for this is C. If density of body is greater than density of fluid, it will submerge. It will submerged. If density of body is less than density of fluid, it will float. And if density of body is equivalent to density of fluid, then free surface it will submerge, but free surface will means just touching this the top surface will just touch the free surface of this liquid like this. So C is the answer. Uh, this is more related to surface tension again. Okay, you try to solve this also. Anyway, we have studied now. Try to solve. I've explained now vapor pressure on concave side compared to your coin, anything you can take. Concave side it is greater, no? Concave side pressure is greater, na? I've already explained. Okay. Next question, 94. Yes, it is viscosity. The property by virtue of which liquid opposes relative motion between different layer. Between two layer, if there is a resistance, between two layer of fluid, if there is a resistance, this is because of this viscosity only. Okay. Next question, 95. This is just a general knowledge type of question. Yes. The process of diffusion of one liquid into another by a semi-permeable membrane, it is called as what? Osmosis. It's not viscosity, surface tension, cohesion, diffusivity, all those things are not there. Osmosis we tell. Okay. Next. 99. Obviously, with increase of size of the tube, like this is the thing and this is your fluid here. And if this is your tube, and let's say I will take a larger diameter tube, obviously in this case there will be more rise, but in this case there will be lesser rise. So rise or depression, it will depend upon that this size of the tube. If diameter is increasing, then the rise or depression will decrease. So D is the answer. That's why for capillarity we should have very, this size of the tube should be very less, no? Small. Size of the tube should be smaller. Okay. 100 question, 100. It is Pascal's law. Okay. You see here we have that question itself, that equation itself. From here also we can answer. Yes. A is the answer. Okay. This though we have solved actually. Yesterday itself we have solved this question. This also. Piezometer also. Okay. From here means we have solved till here yesterday, I think, till piezometer. This question, barometer, this thing we have solved yesterday itself. Okay. And then we have solved this up to piezometer. Piezometer is used for measuring this very low pressure. For measuring very low pressure, we use piezometer. Now this is more related to some that numbers with speed of sound, all those topics. So that will deal later. We'll start from this one, manometer. Manometer is used to measure. See, I've explained already this thing. If this is a pipeline and some fluid is flowing, if you want to measure very low pressure, you put this piezometric tube. For piezo, with the help of piezometer, this fluid will rise here. This fluid is flowing, and it will rise here. So this height, with this height, you can measure the pressure. But this will help you. The piezometer. This tube is what? Piezometer. So with the help of this piezometer, actually this height from center to this one. So this piezometer help you in measuring the measuring very low pressure. But if you want to measure very high pressure, then what you do? You you use manometer. So manometer can be used for very low pressure also, or any high pressure fluid also. Okay. So manometer is used to measure pressure in a pipeline or channel. But if it is like this thing, if you are telling difference of pressure is measured with the help of differential manometer. It is not a simple manometer. This is simple manometer. I've explained already. There is a different types of manometer: simple manometer and differential manometer. For simple manometer, it helps us in measuring pressure at any point. At any point, this manometer will help you in measuring the pressure. But if you are using differential manometer, then you will able to measure the difference of pressure at, between 2 points. Okay, so answer for this one is pressure in pipeline or channel. Clear? Okay, now next 129. This I have already told you, that micromanometer inclined is more accurate compared to YouTube one, but then I have explained, no, there is one more micromanometer that is more sensitive, highest sensitive, more accurate. So this is the micromanometer which is highest, which is having highest sensitivity. Okay, now this 130, this also I have explained. The sensitivity of inclined tube, see, this is your, this is the actual sensitivity, means how much the fluid will move in this tube. Okay, you will measure this thing, this height, but how much fluid will move in this tube? Because what happens, why we use inclined manometer is, when you use YouTube manometer, the movement will be very less in this direction. So if you are using this inclined manometer, no, with a small disturbance also there will be a movement of fluid here. Okay, so main sensitivity is how much fluid is moving in this tube, which is the S. So S is the basic thing which tells you the sensitivity of this thing. So S is actually what? H2 by sine theta. So the sensitivity is 1 by sine theta time. Okay, it is 1 by sine theta time. So we most of the things we actually learn from by solving numerical only. Okay, so answer for this thing, like not numerical, solving MCQs. So 130, answer to 130 is 1 by sine theta. One 133. Are you okay with these questions, or what do you feel? Are you okay with these questions? Is it helpful? Because what I feel is mostly they will ask this type of question only, because 1 minute is there, no, in 1 minute, like you see your gate 1 mark question, there also they do not ask like mostly there will be conceptual question only in gate also, in 1 mark question. Or if it is numerical, a straightforward formula based. But this thing will help you in clearing your concepts, your doubts, your concepts. Okay, next 133. Yes, 150 minutes, 160 question. Hardly 1 minute you have. Yes, center of pressure compared to CG, it is below. This is again the question of that submerged wala means force on a plate. So some pressure is there. So center of gravity will be here, but center of pressure CP will lie below this thing. Center of pressure will lie always below the center of gravity. I have already explained this thing in last class. Okay. So center of pressure will always lie below center of gravity. I have already explained this thing. This is your center of gravity. This is your center of pressure. Always lie below. Okay. 134. We have solved this one already. Yes. Center of gravity. GM, na? GM. M is anyway meta center. G is center of gravity. One 35. Yes, it is C. Repetitive question, but they are here it is asking in different way. That's all. 136. Yes, center of pressure of a surface subjected to fluid pressure is a point on the surface at which resultant pressure acts. Center of pressure is the point where resultant pressure acts. Okay, so A is the answer. Buoyant force. Yes, equal to volume of liquid displaced. Next question, 138. When we were calculating buoyancy force, what happened to horizontal component, horizontal forces? Yes, it is C only, 0. They cancelled out, no? Equal from both the side. From here and here it was equal. So they cancelled out each other. So it is 0 only. I've explained, na? So horizontal, only the difference of vertical and vertical, if it is F1, this is F2. So F2 minus F1 is your buoyancy force. Horizontal component cancel out each other. Okay. This force of buoyancy depends upon. Again, here same question is there. Mass of liquid displaced or that one. If weight is given, then that is more appropriate. 140. Yes, so the line of action of band force acts through D, centroid of displaced volume of fluid. Center of buoyancy is, now quickly answer, rapid fire. 141 A, centroid of displaced volume of fluid. It is like different way of asking same question. 142, body floats in stable equilibrium. B, metacentric height is above G. 143, anyone? You did some mistake, I think. You see, in air, it is 3 kg, m into g. So 3 into g, weight in air. Weight in inside the water when it is completely submerged. Okay. So 2.5 multiplied by g when it is submerged. So I've told you this, there is a difference. It earlier in air it is 3, out inside it is 2.5. So this difference comes because of what? A buoyancy force. A buoyancy force is acting in upward direction, FB. Outside it is 3 kg, but now it is showing 2.5 kg. That means something is pushing upward direction, which is buoyancy force. So the difference 3 minus 2.5 is your buoyancy force, obviously multiplied by g. Okay, so 3 minus 2.5, so it is 0.5. 0.5 multiplied by g is your buoyancy force. Now buoyancy force is given as density of fluid multiplied by volume. Okay, density of fluid multiplied by volume multiplied by your g. Okay, and that to submerged volume. Now this g can be cancelled out. Now this is, now we have to calculate what? Specific gravity. Okay, so but here it, one more thing is there. It should be, that I can write, but density of solid body is not given, I think. Hmm. Density of solid body is not, because here this Vs is there. Now that Vs is like this, I can write this 0.5 is there, which is mass. Mass can be written as density of body multiplied by volume. Okay, so I can write this as density of body multiplied by volume, and again G anyway it is cancelled out, so rho B multiplied by Vs. So this anyway will cancel out only. Sorry, this will cancel out only. So that either one more thing is required for calculation. One more data is required for complete calculation. Okay, I will check this question, and then in next class I will explain this one. If any data is required, I will tell you, okay, in next class. But something else is required here. For specific gravity, they are asking now density. Either density of body is required or volume of that piece is required. Something is required here. Or we'll have to find one more equation. Okay, I will tell you in next class this particular thing. I will check the question one more time. Okay. Next, two more questions, just two more, 144 and 145. 144. You see here, sahi khula hai. Okay, you see this is your inclined case. Okay, if it is this theta becomes 90 degree, then it will become vertical. Okay, now what is the formula for force? Rho multiplied by G multiplied by area multiplied by Hg. Okay, so Hg is from free surface. If it is vertical like this, if it is this vertical plate, then G will lie here. So this is your Hg. And if it is lying, if this free surface lies here itself, then this will become your Hg, half of this. Okay, so the formula is rho G A Hg. Okay, distance of free surface from the center of gravity. Now let's come to this thing. So this is your vertical wall. Okay, is subjected to liquid whose specific rate is W. Pressure is on one side. If H is the height of liquid surface, so let's say this is the height of liquid surface. Like let's say this is your wall. This is your wall. And let's say up to here only fluid is there. Up to here only fluid is there. Okay. So this is the height of fluid. So all pressures are acting like this. So how you will have to consider only this much portion in your calculation. because fluid is exerting force on this much portion. This is not considered in your calculation because no fluid is there to exert force. So you can assume that this much wall only is considered and free surface is here. So free surface is here. So half of this will be your Hg. This is your Hg, which will be h by 2 only. Hg will be h by 2 only. Now your force will be what? Density multiplied by g multiplied by area multiplied by hg. Okay, now rho into g is what? W. Okay, then multiplied by area and then multiplied by hg. Okay, now area, this projected area. Okay, let's say it is given per unit length now, so inside this thing you can take unit length. Okay, and this height, this thing is the projected area. So this area is what? Height is h. Okay, again बहुत कचड़ा हो गया उधर. I will just make like this. This is the free surface, so it will be something like this. Okay, so height is h from here to here, height is h, and this is unit length L. Okay, so this area is what? A will be what? H multiplied by 1. So it will become W into H multiplied by 1. And Hg will be what? Here, centroid distance, which is half Hg, which is half of H by 2. You put it H by 2. So this will become WH square by 2. So the answer will be which option? C. WH square by 2. Clear? Now last question. This I have told you to remember actually. This I have told you to remember. This shortcut. See, pressure acts like this now. I've explained. Here it will be 0. It will be like this. Pressure. Here it is 0 and here it is maximum. So where the center, see, total pressure on wall is above case at following distance from liquid. So total pressure, where it is acting, it is being asked here that where the total pressure is acting. You see center of gravity is this, which is half of your h by 2. Hg is h by 2, which is center of gravity, Hg. But Cp, where is Cp? This is your Cp, center of pressure. And where the total pressure acts, here it is asked that the total pressure on wall, where it is acting from the free surface. So this is your Cp. This is not your G. So Hg is h by 2, which is center of gravity, but Cp is below this. So it will be the centroid of this triangle because pressure acts like this only, no? This is 0 and this is maximum pressure P. So where the centroid of triangle lies? Center of triangle lies height 2h by 3 from above or h by 3 from below. If they are asking from below, it is h by 3. If they are asking from free surface, it is 2h by 3. So h by 3 is also in the option, but it would be the answer for the case when it is being asked from the bottom. If it is asking from the top or free surface, 2h by 3 should be the answer. Clear? So you should know the difference. You should make it very clear whether it G is asked in the question or CP is asked in the questions. Okay, then we'll end the class here. We'll meet in next class. We'll try to solve few more questions and then we'll start our fluid kinematics and then related questions. Okay, thank you. Good night.